divisors of 0 if A and B are two non-zero numbers elements of a ring such that AB is equal to 0. And again, whenever there's nothing, no operation, usually you assume it's kind of the second operation, like in multiplication, for example. So if you have two non-zero elements of a ring such that the product is 0, then A and B are divisors of 0. Or 0 divisors. So if A and B are two non-zero elements of a ring such that if you, under that second operation called multiplication, if that's 0, then A and B are divisors of 0. And next we have a theorem. In the ring Zn, and any Zn for any n is going to be a ring. The divisors of 0 are precisely those elements that are not relatively prime. Remember, two numbers are relatively prime if they don't have any common factors. So if they do have, this is saying that the divisors of 0 are precisely those elements that are not relatively prime to n. So for example, let's take this example here. So consider, say, Z9. And of course, Z9 is 0, 1, 2, 3, 4, 5, 6, 7, 8. Then let's see the numbers that are not relatively prime, ones that have common factors. Of course, 9 is 3 times 3. So the only ones that would have common factors are ones that have factors of 3. So those would be, say, 3. I guess 3 and 6 are the only ones. So 3 and 6, let me pull this out just a bit. See if we can adjust this a little bit. So 3 and 6 are not relatively prime. Now that doesn't necessarily mean every combination of 3 and 6 will end up being 0. To 9. And so these would be the numbers. So although maybe in this case they are. So if you take 3 times 3, that's going to give us 9, which is going to be 0, mod 9. If you take 3 times 6, it's going to be 18, which is going to also be 0, mod 9. 6 times 6 is 36. Also, yeah, I guess in this case, they all the combination are, but it's not always going to be that every possible combination of these numbers will give you 0, but at least each one of these will give you 0 in some context. Let me see if I have another one here. So let's do this one here. Consider Z8. Again, that's going to be 0, 1, 2, 3, 4, 5, 6, 7. And so in this case, then 2 would not be relatively prime. 4 is because it has a 2 in it. 6 is not relatively prime. And so those would be the ones. And let's check all these. So 2 times 4, of course, that's going to be 8. That'll give you 0. Mod 8. And of course, 4 times 6 will give you 0. Mod 8. It's going to be a pretty big mess. That'll give you 0. 4 times 4 will give you 0. 2 times 6 will give you 0, huh? 2 times 6 will give you 12, which is going to be, what, 4 mod 8. So not every possible combination, but at least each one of these will give you 0 when it's multiplied by something else. So in this case, you can see 2 and 4 gave you 0, 4 and 6 gave you 0, etc. So these are the 0 divisors. Any question on that? So again, it's any numbers or any elements, and when you multiply 2 of them together, you'll end up with 0. Again, we're not used to this with real numbers, because real numbers, this never happens with real numbers. If it did, we couldn't solve basic equations. Like, for example, we know in real numbers, so let me do, for example, here, for real numbers, we have no 0 divisors. Otherwise, we couldn't solve if you were given, say, something like x minus 3 times x plus 4, we couldn't guarantee, because we always depend on the fact that if we multiply these two things together and get 0, we know this has to be 0, this has to be 0. Again, that we have always depended upon that in real numbers, but not all structures have that property. Any questions on that? And let's see. Then, and of course, for the z ends, if the n would be prime, and let me call this I have it listed as a corollary. They're really messy. The corollary. If P is prime, then ZP has no zero divisors. Because everything would be relatively prime to that. Again, because everything in the set would be less than P. And so if P is prime, then everything in the set would be relatively prime to P. And one more thing is, a lot of these won't have time to prove, but the cancellation laws hold in a ring. If and only if R has no zero divisors. Like I said, you can call them zero divisors or divisors of 0. Then one more final thing. We have one more structure called an integral domain. An integral domain D is a commutative ring with a unit and containing no divisors of 0. So notice that this is not quite a field because it doesn't say that that every element is a unit. So this is not quite a field. When I gave you the definition of a ring the other day, I realized one thing was missing, And that thing that was missing was closure under multiplication. For a ring, we do need closure under multiplication. I'd gotten the definition of ring from a famous textbook, but it seems they left that out. And so I just wanted to mention. So the one thing I added, and so I just want to show this to you here. For some reason, this is usually I try to take the definition straight from a text. This is a pretty well-known text that's been used for years, but for some reason, I double-checked this over and over. The definition I gave you last time was straight from here. They say they have a definition of ring that's a billion group. Multiplication is associative, and the left distributed law and right distributed law hold, but they don't mention closure here. So I thought maybe you could get closure from one of these other properties since they didn't include that. And I read through this whole section, and they never mentioned closure, but I realized you can't get closure from here. No matter how you I thought, well, if, like, say, for example, if this is an abelian group and you keep adding stuff together, that's similar to multiplication. And so I thought, well, maybe you could somehow get closure under multiplication from that, but you can't in all structures. So really, when they did this really you should have maybe like a fourth property. So when I gave said we should put like a closure is going to be required. And like I said, I'll have that on that handout they give you, but we do need to have closure under multiplication. So a ring has to have those four properties. It's like I said the other day, abelian group, multiplication associative, left and right distributed laws hold, but we also need for it to be closed under multiplication. Any question on that? And like I said, on that little chart I'll give you, it will have the closure included. So let me actually go through some problems just to give us some things to work on here. Say number three, let's go with number one. So 12 times 16 in and 12 times 16. $192. So 12 times 16 is 192. And let's see, under Z24. So let's see, that'd be let's see, 96. Actually, that should be 0, huh? Is that right? Under Z24, I believe is 0. And let me do the next one. 16 times 3 is going to be 48. Under mod 32 arithmetic, that's going to be a 16, huh? And so that works very similar to what we did before. And let's take a couple others here. So let's take a look at maybe number 7. So let's think about this, see if number 7, if this is going to, is this a ring, a division ring, etc. So NZ, first of all, is this a ring? And so we can do our subring test. So if we take any two elements, so if we take, let's say, let n, let me call this n1, n2 be in nz. Then we have to test is n1 minus n2. That's got to be, the difference has to be a multiple of n. So let's say that's going to be mn. So this difference, if they're both of the form nz, then the difference of these has to be some multiple of n. So that's going to be an nz. And the same is true if we take, so that was, remember, that was the first test for a ring. If we take n1, n2, that's also going to end up being some multiple of n. And that's also got to be in nz. So it is a ring. And also the members of z are going to commute. So it commutes. So again, from these two tests, we have that it's a ring. And we know that the members of integers always commute. So it commutes. And answer the question, does it have multiplication?
Yeah, so if n is equal to 1, then it does, but otherwise it doesn't.
You're right. Yeah. Yeah. Thank you. Yeah. So no, unless, like you say, yeah, very good answer. No, unless n equal 1. Yeah. Good observation. So so it doesn't have an identity. That means we can't talk about units. So we can't talk about being a division ring or anything like that. So I think all we can say is a commutative ring then, huh? Looks like that's going to be the farthest. So this is going to be a commutative ring. And nothing more. Any questions on that? Let's take a look at some more interesting ones here. Let's see, how about 11? Let's take a look at 11. So once again, we can assume. So 11, let's think about this for a second. So yeah, so 11. So the real numbers are a field. So we can use the sub ring test. So they're a field in it, which means they're also a ring. Therefore, also a ring. And so we can try the subring test. So if we let's say, two elements, let's say call them X and Y, be in our set. In our set, we're calling A plus B square root of 2, such that AB is in Z, like this. So let's see if we can, so if we take two of these, so that means X is going to be, let's say, A1 plus B1 square root of 2. And Y is going to be A1 plus B1 square root of 2. And so if we do, let's also, okay, let's do A1 plus B1 square root of 2 minus A1 plus B1 square root of 2. Excuse me. The second one should be 2's here, sorry. This should be A1, B1, A2, B2, A1, B1, A2, B2. And so we'll have A1 minus A2, and we'll put these two together plus B1, B2, square root of 2. And so the question, so this looks like this is an integer here. And this is an integer. So we took two typical elements in the set and proved that we got the same form of something in the set. So I think we can say that that's in the set, huh? So therefore, so that was the first test for subring. And so how about if we do the multiplication, A1, B1, square root of 2, A2, B2, square root of 2, A1, A2, plus A1, B2, square root of 2, plus A2, B1, square root of 2. Now we multiply these two together, this times this. The two square roots will end up being 2, so it'll be plus 2 times B1, B2. So that looks okay. And then let's see. Yeah, so we're going to end up having something in the same form, huh? Because we're going to have these two here. Just A1, A2, plus 2B1, B2. Plus A1, B2, plus A2, B1, square root of 2, huh? That looks, so we had, once again, more products of integers or integers. So here we got an integer again. And integer times square root of 2. So we still have something. So we multiplied two typical elements in the set and still got another element in the set because it has the same form. So this is going to be true. And so this is going to be a ring. And also a commute. So it's going to be a commutative ring. So we have that so far. Any question on that? We have a commutative ring. And the next question is it a field? And we can use our subfield test. Now, one thing that we can maybe think about, well, first of all, that one thing, let's remember, yeah, okay, this time we do have an identity. So identity is going to be 1. So let's try our subfield test. One thing in the subfield test was that we had the first part's already taken care of. Subfield test. Remember, we have to have like that. The two elements have to be in the set if we subtract them. But the other thing we're going to need is that we need the two elements times the inverse to be in the set. So let's see, let's think about that for a minute. So the question is, if we take our two elements, say x equals a1 b1 square root of 2, and we have our y, let's say we take another, let's say we want a y inverse. How do we want to say this? Maybe say, so we have an x here. Can we find an x inverse? Say of the form a2 b2 square root of 2. So the question is, can we find something that when we multiply these two together, that we will get 1 here? Just think about this. So in other words, this would be like our x and x inverse. So if we multiply, let's go through and multiply these out. And we actually had done that previously. So let me copy that from our last step. So this is going to be 2b b2 plus a1 b2 plus a2 b1 square root of 2 is going to be 1. And so for this to be true, we're going to need for this to work out to be 1. Now, obviously, the first thing we're going to have to do is what this has to be 0, doesn't it? Because we can't have a square root of 2 here. Oh, well, the other possibility would be for this to be 1 to have a square root in it that would cancel, but these are just integers, so that's not possible. So we need this to be 0. So need to be equal to 0. So if we do a1 b2 is equal to negative a2 b1. And so now we're given the a1 b1. So we're going to have to find like a b2. So b2 is going to have to be equal to, let's call it negative b1 a1 a2. So again, these are the b2 and a2 are the unknowns, because we're given like our a1 b1. And so this is the relationship that we have to have for this to work. We need, and that's only going to work, let's see, because the answer has to be an integer. So this really can only work if this is A1 or some multiple of A1, huh? That's about the only thing that'll work. But that would be possible, but then also over here, so we need this to be 0, then we need this to be 1, huh? So needs to be 1. And let's see. So let's, will be the best. Obviously, this isn't going to work. I'm trying to think of a best way to kind of show it. So if we put this over here, A1, A2 plus 2, B1, and then I'll substitute for B2 here. Negative B1, A2, A1. We want this to be equal to B. We want that to come out to be 1. And so this is going to be A1, A2 minus minus 2B1 squared, A2, A1 equal to 1. Again, the unknowns, now this time the unknown is A2. And so let's solve for A2. So A2, if we factor A2 out of here, that's going to be 1 over A1 minus 2 B1 squared over A1, if I'm doing this correctly. I probably should put the extra step. What I did, I factor out the A2 and divided by this mess. And so obviously, this is not going to be an integer, not in at least not in every case. Not an integer. In fact, probably in the vast majority of cases. So this is not a field. Not a field, not a subfield. Any question on that? That's pretty messy. So again, going back, I probably should have had written down just the way we had it before. Last time we talked about the subfield test, and we said that we had the subfield if we had a subfield if we took any two elements in the subset that they were in the set, and that's going to be satisfied. Then the other property we need for a subfield is we had to take any two elements that the inverse, like say let's see, AB inverse. Okay, well, I guess what I'm sort of showing here is that this was not even, yeah. So this, I guess I sort of more or less just showed directly that this didn't have an inverse. That maybe I guess I'm really not using the subfield test. But so, in other words, so I tried to find, so I had a typical X, and I wanted to show, find out if it had an inverse or not. So I multiplied it at something in another form and see if we could find elements to make that equal to 1. And in this case, we can't. Any question on that? I realize that's pretty messy. So now the question is, then if we look at the look at the very next one, this one says A and B are in the rationals. So now the question is, would this work if A and B were in the rationals? what could go wrong this time? If anything.
Like it's like the A2 thing was fine, right? Like, cause that big mess thing is just like subtracting and dividing and stuff, so that would still be a rational number.
I think it is, yeah.
But then like up top, calculating B2 based on A2, we basically had to have A2 be like a multiple of A1, otherwise B2 would be, like it wouldn't work out, right? Or does that still work?
Okay, if you had rational numbers, you would have to have the A1, B2 plus A2, B2, and B1 has to be 0.
I didn't hear that last part.
It's equal to 0. The integers like square root or something. Like, did that mean if it was all rational, but have something other than 0?
No, I think we'll still have to get rid of, since the square root of 2 would be irrational. Right, I think we would have to still get rid of that, but it's a good thought though. But yeah, I think we still, now if it, oh, go ahead.
Wait, but it actually is still fine though, because B2 can be any rational number, so the fraction doesn't actually cause any problems.
I think that's right. That's right. The only reason we were kind of thinking before is because we didn't want a fraction at all here. Yeah. So I think this one does work, huh? And then the question, so now to fully do the subfield test then, let's see. So how messy does this? So in the case of so in the case, so here for 11 it didn't work. So now for again for what is this 12? Each element does have an inverse. That we just showed. And now the question, and this is the part that would get really messy, huh? Because for the subfield test, we technically need that, let's see, A, B inverse. Well, let's see if we can do this. Okay, so what we found up here then was that the inverse, so the inverse is of the form, let's say over here we have, let's say A2 was 1 over A1 to B1 squared A1, and B2 was this mess here, square root of 2. So that's the inverse. And if we took, like, say, another element times the inverse of that element, again, we're out of time. I think it's going to be in the set. It's crazy as it looks, huh? Because we're just going to end up having, let's say if we took another element, let me call it A3 plus B3 square root of 2. If we took it times this inverse, we're still just going to end up with, unless I'm missing something, we're still just going to end up with fractions of stuff. And we'll have like in this, we'll end up just, in one case, we'll end up being 2. In another case, we'll end up being square root of 2 times some numbers. So I think if we did the subfield test, if we took this times any other inverse, we would still end up with an element in the set, it looks like. If that makes sense. But we're out of time for me to actually formally show that. But it looks like, so in the case of in the case of 12, then it looks like that looks like that is a field. So I'll put a question mark because we didn't go through, but I think it is gonna work. So I will stop there and